Hey folks, so today we are going to discuss Leetcode problem, convert sorted list to binary search tree. So in this problem we are given a head of single linked list and all these values are present in an ascending order in the linked list. As you can see, like -10, -3, 0, 5, 9, all these values are in ascending order and we have to convert it into a height balanced BST. Okay, so height balanced BST as in at any stage in a binary search tree, you will not have the left subtree and the right subtree's height difference to be greater than 1. Okay, let me give you an example. So if you can see in this problem, once I convert this linked list into this binary search tree, at this node the height of left subtree is 2, right, and the height of right subtree is also 2, so the difference is 0, right? And if you consider this node, the height of left subtree is 1 because we only have one node, and the height of right subtree is 0 because we don't have any nodes here, right? So the difference is 1. And if you take this node, the height of left and right subtrees is 0 and 0, right? So the difference is also 0 here. And similarly, the other nodes, it's 0 and 1 here. So this binary search tree is balanced, right? According to the definition of height balanced binary search tree. So that's what it is all about. We have to convert the given linked list into this height balanced BST and we have to return it. Okay, so that's the entire problem, guys. So when I started thinking a solution for this problem, the first thing that came into my mind is like, it's very inconvenient to deal with linked list and convert it into a binary search tree in one go, right? Because of two reasons. First, I don't know the length of the linked list at any given stage until I reach the end of the linked list from start, right? So I have to traverse through the entire linked list and then find the length, and I have to store the length of the linked list. So that's one inconvenience that I have with linked list. And second thing is, once I go from first node to the second node, I cannot come back that easily, right? And that is also a problem. So these are the two problems that make me inconvenient, and that's when I felt, okay, why cannot I use an intermediate data structure so that it becomes easy for me to convert the current list into that intermediate data structure and then navigate from that data structure to the binary search tree that we want. And the simplest data structure that we know is list, right? So then I've started converting this entire linked list into list first in the first step. So convert it into list, and I got my values here. And then I started thinking how I can convert this list into a height balanced BST. So how to use this list to convert it into a binary search tree? This is the first question that I've asked. Okay, forgetting about the height balance thing for some time. And what I came up with is, consider the middlemost value and use it as the current node. Okay, and consider the left values to the current middlemost value as the left subtree values. Okay, and I'm using it as -10 and -3 here. Okay, and then I can use the right values to the 0 value as my right subtree of my current binary search tree, right? That is 5 and 9 here, right? And if I use the same ideology for both left and right subtrees, what it will happen is, for this list, it will be -3 here and 10 here, -10 here, right? And for this right subtree, it would be 9 here and 5 here, right? So that's when I felt, okay, this is giving me directly the height balanced binary search tree. And I have used the same logic for couple more different inputs. Let's say I have 6 values instead of 5 values here. So let's say I have -10, -3, 0, 1 and 5 and 9. In this case, the middlemost value would be at the index 3, right? So the 1 value will be here, and all my left values, that is -10, -3 and 0 will be coming here, and right values will be coming here, right, 5 and 9. So let me quickly erase this part. So if I have to convert this binary search tree into the next step, then what I'll get is I'll have 1 here, and if I have to change this in binary search tree, then I'll be getting my middlemost value here again, and the left values here, and the right values here, right? And similarly it applies for the right subtree as well. So 9 comes here and 5 comes here. So this is what I have implemented for my height balanced binary search tree as well, guys. So let me quickly explain what I have done in 2 steps. So firstly, I've converted linked list to a list, right? This is the first step. And second step, I have recursively gone through the list, and using the binary search technique, I have converted the list into a height balanced BST. Okay. So these are the 2 steps that I have taken to come up with this solution, and let's jump into the code. So if you can see here, guys, this is my code. We are starting off with this function, and these are the base cases. So the first base case is talking about the condition where we have an empty linked list. So in that case, we are just returning in null node. Okay. And in the second case, we are having only one value in the linked list, right? Let's say it's 0. Then we have to create a tree node of this 0 value, and we have to return the tree node, right? So that's what we are doing it here. And once these 2 base cases are done, we are moving into the actual main part. So here what I'm trying to do is I'm taking an empty list here and calling it as my list. So once I'm done with that, I'm converting my linked list into list and adding all the linked list nodes step by step to my actual list that I've taken here. Okay, once this whole while loop is done, I have converted my linked list into a list, right? And I'm calling it as my list here. And so after this step, I'm trying to call this function where I'm converting the list to BST, which is height balanced binary search tree. And for that, I'm taking this function list to BST, and I'm passing my current list, that is my list here. And these are the starting and ending indices. Okay. So as I've told you, I'm recursively performing the binary search operation on the list to find the current node at every step, right? So for that reason, I'm taking start and end indices of this list, okay, and I'm sending it to here. So in this function, what will happen is if my end node is greater than start node, then I'm returning none. I'll explain you why in a little while, okay? And just as any binary search tree algorithm, we are calculating the mid value. So let me take that example: -10, -3, 0, 5 and 9. So initially my start will be pointing to this, and my end will be pointing to this, right? Once I'm done with that, my middle will be pointing to 0, right? And then I'm performing a recursive operation by creating a tree node here. Okay, tree node value is my list of mid, that is the current node will be having mid value 0, and the left of this tree node, as we have defined tree node here, the left, I am pointing it to the subtree that we will be getting from -3 and -10 and -3 respectively, and the right pointer we are pointing it to whatever subtree that we will be getting using 5 and 9. Okay, and when we are calling this function, so it will convert this entire left list into -3 and -10 as we have seen, and it is returning this entire subtree to this, right? So at this stage, what our binary search tree will look like is 0, -3 and -10. Okay, So once this is done, and when we go to this, it will convert this 5 comma 9 into 9 and 5, this subtree, and it will return this entire subtree. Okay, so it will look like 9 and 5 at this stage. So once this entire step is done, which is at the 17th line, so we are getting the node pointing at to this node. Okay, this entire subtree, both the subtrees are ready, and we are pointing it to the root node. Okay, and we are returning the root node after this step, hence getting our final answer. Okay, but in the recursive process we have to end somewhere, right? So when we are going in the same way, once we are getting our root value, we are going to separate the entire list into three things. So one is our left subtree and the right subtree and the root value itself. So when we are recursing through the left subtree of this entire list, that is our start and end values now become start as here and end as here, because our end is point nothing but mid minus 1, that is this value, and our start is the same start value. And for the right subtree it is 5 comma 9, and this is the start value and this is the end value, right? So for this step, once we go one step further, then our middlemost value will become this, and this is our mid minus 1. So when we call this list to BST function for the left subtree of this particular list, then it will be minus 10. So the start and end will be pointing to the same thing here, because this is our end and so this is our mid and this is our mid minus 1. So mid minus 1, and our left subtree for this particular list is having start to end, that is mid minus 1, and the right subtree will be mid plus 1 to end, right? The end value is at pointing at this position, that is 1, and mid plus 1 would be something here, right, which is index 2, and ind 1 will be our end value, right? Since in this condition the end value is less than start value, right? The end is pointing to index 1, but the start is pointing to mid plus 1, right? In that case we are returning the null value. That means for minus 3 here, the left subtree will be having minus 10 and the right subtree will be having nothing. Okay, so this is the null value here. So that's where this base condition helps, guys, and that's what I wanted to explain. And yeah, that's pretty much about it. If we talk about the time and space complexities here, the time complexity is going to be order of n, since we are traversing through the entire list and that too only once, and the space complexity is going to be order of n again, since we are using a separate list. That's for this video, guys. If you like this video, please like, share and subscribe to my YouTube channel. That will really keep me motivated to make more videos. Thank you.